Okay. This is a quick stream, guys. Just doing a stream on demand. Someone wanted to see Sagittarius, so I figured I'd stream for a bit and show some of the gravitational lensing and some of the other effects. I've turned my graphics settings up higher again, and I'm now at full resolution. Hopefully the stream works well at that resolution. I don't know if it will, but we'll find out. So I'll just say a few things. Sagittarius A star, it's a supermassive black hole, a few million star solar mass. There's large amounts of lensing that you're going to see, gravitational lensing, even from large distances. For those who don't know what gravitational lensing are, it's light travels on a geodesic of space-time, a straight line in flat space, but if there's gravitational curvature due to masses, the light will actually bend along that curvature, and if the mass is great enough, if the curvature is great enough, then you can actually see light bend around in circles, and if there's a source of light behind the mass, it can actually lens or split the image into multiple images. So you'll see the same star twice. So for instance, the one I'm looking at right now, the brightest one on the left and right, you can see very clearly. That's the same star actually that's behind the black hole, or some angle nearly behind the black hole, and it's lensing it. So this will normally happen close to dense objects or high mass objects. There's some gravitational lensing that you can see from the sun, and actually there have been numerous experiments to verify that the lensing happens the way general relativity predicts, because the lensing that's expected in non-general relativity is different from the amount of lensing that you'd experience in general relativity. And there have been numerous experiments over time. There was one in, I think, 1917 by Arthur Eddington. There were a few others later that were more accurate, and I think statistical accuracy that was high enough to verify that it was indeed, GR was indeed correct in its prediction of gravitational lensing. And so this is verification of that. Well, this is not verification of that at all. It's a game. But if I were to say this was real life, this would be verification of that on an extremely strong field gravity, which is one of the questions that they have in physics. Is GR is expected to be good in possibly all regimes of gravity, whether it's weak field or strong field. Obviously, for extremely weak fields, Newtonian gravity approximates what's happening. In stronger fields, stronger masses, there's more warping and general relativistic effects. It's possible that in extremely strong field gravity, that even GR is only an approximation of the true effects that you see in the universe. And so if we were to be looking at this in real life and be able to test the lensing on the supermassive black hole that has this high of a gravity, it would be a great test of that. And there's some tests similar to this where they're looking through observatories that are on the ground, are looking at stars that are nearby the black hole, supermassive black hole, Sagittarius A, and by looking at the orbits and how the orbits are changing, they can test how extremely strong field gravity interacts and test general relativity in that regime as well. So there's some effects here that Elite Dangerous does well. The lensing is one of them. I think that it pretty much ignores any sort of accretion disk or hot gas emissions. The Sagittarius A star is a relatively inactive black hole, meaning that there is relatively little matter quite near it that it's actively tearing apart and consuming, to use a humanist term or an anthropomorphic term, but it doesn't show any, which I think is fairly inaccurate. But there's some limitations, I think, due to graphics issues and the fact that it would take a while to program that. So I can approach the black hole, I think. Let's see, how close am I to it right now? I'm 250 light seconds away, which is, if I recall correctly, that's about 1 AU. So let's see, 1 AU, which is the distance between the Earth and the Sun, it's about 7 minutes or so away as far as light travel. And 7 minutes would be what? That would be 420 light seconds. So 420 would be 1 AU. So I guess we're at about 1/2 an AU here. Oh, sorry. I think someone is asking some questions here. Ah, okay. Maybe not. Oh, I'm not even looking at the stream, so if someone's typing questions during the stream, I'm sorry. I didn't actually have it open right now. And I apologize. But if you message me, I'll answer them on the next stream or something. This was sort of a spur-of-the-moment stream just for someone to see the effects in-game of the black hole. Let me actually go into Super Cruise so I can get up close. So I've done some analysis on the black holes in game, and some other people might know this, but there's an exact linear formula that the devs have put in that determines the exclusion zone of the black hole, which in no way is based on anything in real life. But there's only so close that you can get to the black holes in the game before you just can't move any closer. It just drops you out of Super Cruise and you just run into this wall. And it's a linear formula based on mass. And I think it's something, if I recall correctly, something like 17 light seconds plus some, like 2 times the solar masses for every light second added. So you can see now extreme gravitational lensing. You can see all these little, what you think are particles almost, warping around it, moving around it, but those are actually stars that are behind and near in the distance, and they're just being lensed. They're being distorted quite heavily. And I'm gonna attempt to come up close to it. Hopefully I don't die. I don't think I would, because I've done this to other black holes in the game, but we'll find out pretty soon. Worst comes to worst, I take a fast trip home. The other thing is, as is shown in the little icon in the bottom left, this black hole is spinning, and it's spinning, I think, reasonably fast. Some black holes spin faster than others. I think probably the stellar mass black holes would have more reason for high spin, because, like the ice skater analogy, if they're coming from stars that already spin, and for instance our star spins once every about 8 to 10 hours, depending on the latitude. It's not a complete solid, so its rotation is variable on latitude. But if you were to compress the star and draw the ice skater's arms in, it'll spin a lot faster. And since a black hole is compactified extremely so compared to if its mass was in normal star form, it will spin quite fast. In fact, it'll spin at near, some of them will spin at near light speed.
Warning, temperature critical.
Aha, so I'm having some temperature critical issues, so I probably need to back out of here before I get in trouble. So sorry about that. Now that I know it's a problem, I will not do that. See if I can get out of here in time.
Warning, temperature critical.
So I haven't had this problem with other black holes, but I haven't been near a black hole in a while, so maybe a new patch at some point changed this. I don't know, honestly. But like I said, if it's a black hole is accreting matter, then it's going to be really hot near a black hole. It's going to accrete matter, and that accretion will create high amounts of friction. And that's why black holes are X-ray sources. One says, well, nothing escapes a black hole. Well, that's true. Nothing escapes once it's inside the event horizon of the black hole. But surrounding the black hole, there is matter. And once that matter is, and as that matter is being accreted and it's being compactified and rubbed against each other at very high velocities, it's going to emit X-rays, gamma rays, possibly even very high energetic photons because the matter is being heated. So, and that's actually how the matter is able to very easily compactify, is that energy can be released through photons, through electromagnetic waves, to allow the reduction in the gravitational potential of the matter, so that it could be eventually accreted by the black hole. And that's why dark matter also doesn't normally clump, is it cannot emit electromagnetic waves, as is the current understanding of science anyway. Alright, so that's a little bit about the black hole and how it is in the game. And I'll stop the stream for now and wish you guys happy flying. Okay, so there's one last question someone asked me on TS, and that was that how many black holes do you know of in the game? I've cataloged over 150 that are near inhabited space. And by near, I mean within 3,000 light years. But there are thousands, if not millions, in this game, which may or may not have real life justification. There are 400 million star systems in the game. 400 million? 400 billion. I confuse myself sometimes. I think maybe it's 400 billion. Alright, well, it's a lot. And a lot of those actually, according to what people have said and FDev has said, is that they've randomized them to include a lot of black holes and neutron stars. And so there are thousands, if not millions, of black holes in the game, especially near the center of the galaxy. Some people have found clusters of 500 black holes within only a few dozens of light years. And again, I don't know if that has justification from real life. There's only a few dozen, if that, galactic black holes that have been at least electromagnetically identified. And some of those might be false positives because there might be another reason for the source of the X-rays that they see. But yeah, that's the story with that. Alright, so I'll close the stream for now, and maybe we'll have another stream later in the week. Actually, maybe tomorrow about Jock Station, and maybe later this week about some SRVing. I know there's also possibly going to be a stream or an event held by Null about engineers, and we'll talk about that further if I get more information about that. Thanks very much.